Um, Here is Chenming and Amrit here to give a short introduction about our dot logger. And this video, I would like to do that since a very long time. It doesn't make it happen, but today we finally make it happen. We also find a lot of technical issues how to show the real-time camera with the screen at the same time, but eventually we make it happen, so that's really good. At least from this screen we can see the command line or also the guideline as well as the monitoring system at the same time. So I would like to introduce the dot logger that we have been producing. It's called pyduino. And the reason why we call it pyduino, as the name says, is because the system is a combination of a Raspberry Pi and a Arduino, right? And what are the difference between the two? Well, Arduino is pretty much like the circuit within a puppy doll. So you just need to put a battery, they do the work for you. And this microchip is very efficient in doing something that is scheduled. Let's say do the measurements or switch on the lights, this type of thing, and they never make wrong. Whereas Raspberry Pi is pretty much like a computer. So computer, you're not supposed to switch it off by pull out the power. You need to shut down first before you do you pull out the plug. And it's obviously much stronger in terms of installing software and also adding different functions, but it doesn't really allow you to do ADC measurement. ADC measurement is pretty much like you measuring the voltage, so it's the analog signal. It only can measure it only can provide power up to 3.3 volt. Instead, Arduino allows you to be able to power by 5 volts. Obviously, Raspberry Pi would be good enough to allow us to log into the system wherever it's been deployed, whereas Arduino will be able to do the measurement very accurately. So that's generally the idea. The advantage for this system is that once you have configured it, you pretty much have the freedom to do everything. For example, you could connect the system with a light and a camera so that you can first switch on the light and do a picture, take a picture and then send it online using SCP command. And you could also schedule all different type of things. Let's say if your pH is too high, you start off doing some switches. So because it's an open source environment, you are allowed to do all the things as long as the input and output allows you to do. So that's the advantage of doing it. Well, the reason we decided to develop this is because many cases we find the proprietary system doesn't allow you to integrate everything all together. Just as the example we mentioned before, if you have a camera, the camera might give you a modem, so you need to buy a separate modem for that camera. But this modem would not be able to provide internet connection to a soil moisture measurement. So you literally have to buy 2 SIM cards and supply separate power to them. Whereas this dot logger, it's so easy to integrate them all together. The second thing is that this dot logger has got a lot of 5 volt switches. So you can see if you see there are so many 5 volt switches. So those switches has got a high side and a low side. So high side is for positive voltages and the low side is ground. So that are able to switch off the sensor, switch off the power of the sensor if you don't want to do measurement, and only switch on the power of the sensor when you do the measurement. And this is important because let's say if you have 500 sensors connected to the system and one of the sensors is short-circuited, and if that system is deployed somewhere very far away, you probably have to go there to pull out that sensor because the whole system is short-circuited. Whereas if you have individual switches, you can just disable that particular switches to the sensor so that you still have the rest of the system running properly. So that is also our advantage for having individual switches to every sensors. So I will give a very, very quick introduction about what the dart logger, what does the dart logger do. So first of all, let's just pull out the power because the Raspberry Pi here is already switched off. So I just pull out the power. Yeah, we probably need to get them later on. So currently it's switched off, and within the system, just leave it here. Yeah, just leave it here. We first supply power, which is 12 volt, to the system, and the power will be regulated to 5 volts, and this 5 volts will supply power to Arduino and Raspberry Pi. And the Raspberry Pi will be able to communicate with Arduino through a serial, a software serial. We are not using the serial at the GPIO because we spare that serial for other uses, such as modems or anything. So we use a serial GPIO. And also, Raspberry Pi is able to send a command that is able to reboot the Arduino. And this is sometimes very important. Let's say you could do some measurements, and then the measurement was failed, and you have to reboot the Arduino. And rebooting Arduino, if you are next to it, is very simple. You just need to click that button, like this. But how about if the system is deployed 5,000 kilometers away from you? You probably wouldn't be able to afford to go there and click the button and go back home. So Raspberry Pi is able to send a command to Arduino and allow it to do a reset. So we will discuss that command later on. At the same time, as we know that Raspberry Pi is a computer, and computers sometimes overthink. So you could have the power on, but it freezes. And if it freezes, the only way to be able to make it alive is to code switch it off and then power it up. And in fact, the Arduino is able to do that by switch on one of the pins and then switch it off again, so that the Raspberry Pi is able to do a cold start. And we regularly do that for all the system we deploy to the field, because in some cases, we just need to have Raspberry Pi to have a regular refresh, so there is no memory going and excessive. Yeah, we just regularly reboot the system, so that is also a plus. And usually you can connect it to the system either through a USB to your own computer. You could also use the Bluetooth from the Raspberry Pi to connect it to your computer. You could also use 3G to be able to connect it to your computer. At the same time, you could also use the Wi-Fi to connect it to the whole dart logger system. So there are so many ways to be able to connect your computer to the dart logger and do any configuration on the go. So this is a plus. Now we're gonna quickly show the dart logger, the pin out the terminals, and you see this takes the majority of the spaces. Before we do that, I want to show you that given that this is version 3, we also got version 2. It's much bigger. It does exactly the same thing, but with a relatively large footprint. And later on, we decided to make this section as make it this side as a surface mounted and put it behind the terminals. That's why the current version takes much less space as compared to the second version, but they did exactly the same thing, right? Also, I would like to say that the dart logger provide two extra functions. One is to measure the ambient temperature and humidity. The second thing is to measure the voltage from the input. Those two things are extremely important when you deploy the logger to the field. So in terms of temperature and humidity, remember that this system will be deployed to the field within the enclosure, where the humidity in the enclosure could potentially increase as time goes. And in the past, it's common to have a plate, a color band, so that when you open up the enclosure, you read off the humidity by looking at the color band. So it's pretty much like a pH tester. But it's a bit primitive because you can only check the humidity inside the enclosure by looking at the color band. So we decided to put a humidity sensor on the board. It measures every single time. So if it reaches around 80% all the time, that reminds you that you need to go there to change the desiccant and then reduce the humidity, because the humidity will eventually damage the dart logger. The second thing, which is also important, is the voltage measurement. So currently, given we are in the office, we can use a power socket to provide power for the system, but we could also use solar power to supply power to the system. And in that case, the input is subjected to change over time. So once the power is reduced to some level, we really need to ensure the whole system is in the dormant condition until the power bounces back again. So that is also depending on the power of the whole system. So you can write some if conditions based on that. So that's the extra two functions here. Now I'll quickly go through the functionality of the data logger by pinpoint the location of the terminals. So this block here, as you can see, is called Raspberry Pi input and output. So basically this section is the pin out of the Raspberry Pi. And if you look at these tiny little pins here, so those pins has been mapped to this section. So by this section, you can either do some digital measurements. You could also make it as switches if you want to. We also provide a ground here as well. So this pin here is a ground. The ground could be used for all different types of purposes. So that's the GPIO part. Now we've got a switch sections. So this switch section has got a power up to 3.3 switches, 3.3 volts. And those switches are controlled by GPIO as well, of the GPIO of the Raspberry Pi as well. For some sensors, it provides 3.3 volts. So you could make use of the GPIO. Let's say if you use this one and this one, this is positive and negative. If you put the positive and negative of a sensor to these two ports and switch on the number 4 channel of the GPIO, this channel is able to provide you a power of 3.3. So that's the purpose of that. And here you also got the 3.3 switches, and these 23, 24, 25, and 26 are basically the GPIO numbers. So if you shoot a switch on for 26, you will be able to provide 3.3 volts to the sensor connected to that reel. Now let's move to the I2C. So you see that there are 0, 1, 2, 3, 4, 7. So there are 8 pair of I2C pins. So what does I2C pins for? As you know that the way how the microcontroller talk to the sensor is the same as how we speak to each other. So we could either use English, we could possibly use Spanish or Japanese, depending on the type of sensor we work. So sensor has different languages as well. So the most popular one would call analog. So analog is similar to you measure the voltage. So let's say moisture sensor, you measure a voltage and you convert that voltage to the moisture content. So that's an analog, directly analog reading. So even a multimeter is good enough to measure the voltage. But there are also some other protocols. So I2C is one of the protocol. So you've got SDI as SCL. So you need to have 2 pins as the communication ports. Within the I2C pins, you would be able to hook up 8 sensors at the same time. 8 sensors at the same time. And later on, I will show you how to connect the I2C sensor. Now, if you move a bit further, you will see you've got the TX and RX. So those TX and RX are the map out from the Arduino, because the Arduino Mega, which we used here, has got 4 pairs of serials. So the TX and RX0 is used to communicate between the Arduino and Raspberry Pi, whereas TX RX 1, 2, 3 are here ready to deploy any types of sensors available. And we've got several digital outputs. So this one is digital output 4, digital output 5, digital output 3, and a ground here. And after that, we have 50, 52, 51, and 53. So those are the digital pins available for us to do any sensor sensor input. So you can read sensor input from these digital pins. And then we've got the analog ranges. So these analog ranges is basically a map directly from the Arduino Mega. So in total, we've got 16 channels to measure analog values. And we actually, one more thing I have to say is that we actually use analog 0 to measure the system voltage. So if you would like to insert an analog sensor, the first one that you should use is not going to be 0, so that it doesn't in conflict with the voltage measurements, right? So this is something very important. So you can start with sensor 1, 2, 3. So leave the 0 for the voltage measurements. Now, this section is basically switches. So they are all output, and they provide 5 volts. So the number 22 here is the pin number of the switch number of the 5 volts. So if you have a sensor might have a positive and a negative. So the positive goes here because it's upside. This is positive, and negative goes to here. So that goes up here. If you switch on the voltage switch on 22, you will see that this 2 rail provides a 5 volt DC for the sensor, and later on you can switch it off. So that provides a advantage. So we got quite a few channels here, so free for you to use. Now we move to the tiny section, and later on we can start playing with the system. Now this one, what they say is reversed 12 volt and 5 volt switches. What does it mean, reversed 12 and 5 volt switches? First of all, the reverse here means that when you don't touch, when you have a 0, so you switch off this output, this channel provides power. So let's say right now the system, if the system is powered up, you didn't switch it on, the 12 volt is already within that channel. But instead, if you decided to change the 0 to 1, and this switch is off. So this voltage, this power supply is best for something that you would like to power them most of the time. So you probably just switch it off intermittently. So majority of the time you switch it on. And this is probably like a camera. You would like to have the camera switch on, let's say 23 hours, and you just want to rest it for 1 hour. So if you would like to do that, you can just allow the pin 13 to switch on for 1 hour, so that within the hour, the power here is off. And the reason why we call 12 volt and 5 volt is because you can use the jumpers on both to show whether you would like to provide 12 volt or 5 volt. So you need to be very, very careful to see what type of voltage has been provided to this reel. So if you, let's say if you would like to power up a 5 volt sensor, instead you provide a 12 volt power there, that will damage the sensor, unfortunately. So be very, very careful when you use the switches here. Now we've got some constant voltage. So this is 5 volt, 12 volt, 3.3 volt, and ground. So at the very bottom, we've got two other switches as well. So also it can change from 12 volt to 5 volt. So just bear in mind that we have 13, 12, 11, and 10 readily to be changed from 12 volt to 5 volt, right? So now I'm going to zoom in the jumpers to let you know how that is being changed. That will be changed the power supply. So I'm just trying to zoom in and see whether the camera is able to pick up the I'm just trying to repeat the process. I'm just moving around and see whether there you go. So you see now within the jump we've got quite a few jumpers here. So the RSW10 with a super score, and you got 3 pins. So now it's been jumped from the middle one with the 5 volt, and the 12 one is left empty. So what does this mean is that the switch 10, which is a reversed switch, is going to provide you 5 volts, right? And similarly, you see that the RSW, so that's called reverse switch number 11, and the overscore, the scores about, I'm just trying to do that again because we can't see the mark very clearly. I hope that it can adjust it by itself. No, not really. Not really. So this is good, but these is not as good as we thought. Oh, there we go. Okay, so RSW11 has got, so we can even see from here. So RSW11, and there is a line on top. So currently you can see that a jumper is jumping the middle one with the 5 volt on left hand side. So this means that the switch 11 is going to give you a 5 volt only. And same likewise, you got the switch 12, same manner. So that provide 5 volt, this also provide 5 volt. Now there are some other things that I would like to say. So you see on the left, so if you switch on the power, the lights, so we want to see the lights using your camera. There are some extra things that I would like to see. So if you illuminate from the top, that basically messed up everything. That's sad. Actually, okay, I think that's good enough. Yeah, that's good enough. So just leave it like that. Yeah. So the very last one has got the Raspberry Pi voltage. So you see that there are also 3 pins. On one side, you got a 3 volts. The other side, 3.3 volts. On the other side is 5 volt. So if the jumper is jumped between the middle and 3.3, that means all the switches for the Raspberry Pi is going to give you only 3.3 volts. And if it's jumped from the 5 volt to the middle, that means the Raspberry Pi switches is able to give you 5 volts switches, right? Now, let's move to the top. The top has got a name of power for Raspberry Pi. So if you jump this one, you switch it on, that means the Raspberry Pi will be powered. So this is normally the case. We need to power the Raspberry Pi, right? Now we've got another blues. The blue TX and RX is basically to connect the connection between the Raspberry Pi and Arduino. So you want them to be able to talk with each other. So usually these 2 pins needs to be switched on so that Raspberry Pi is able to connect it to Arduino. So very important. And now we've got vSense. So this got 2 switches, two jumpers. And usually it's being on by default. And the vSense here is basically to connect the analog 0 to the voltage provided to the system, so that you can use the 0 as a input voltage meter. So you tell what is the voltage of the input power. Now you've got the SW9LV. So this SW9 is basically the voltage provided by switch 9. So currently it's being set as 12, and that means the switch 9 is going to give you 12 volts rather than 5 volts here. And now we've got the switch 8. Switch 8 is currently giving us a 5 volt as well rather than 12 volt. As you can see, it jumps only to the 5 volts. And finally, you've got a ground and G12. What does this mean is that it's a common ground for the power, because this power regulator has provided a function to separate the ground, but sometimes we need to ensure the ground of the 5 volts and the ground of the 12 volts are interconnected, and that interconnection is done by switching on to put a jump in between these 2. So this is normally default on, so it has to be there. So that's all about the jumpers. Now we're gonna do a quick switch on and see how usually the system is going to work. So this is going to be done by putting the power. So normally the power goes in this, and usually before you switch on the power, you need to check the voltage. So we've got a multimeter here. So remember that the positive goes to the left-hand side, and the negative goes to the right-hand side. So it will always be good to check the voltage before we start off doing anything. So currently I'm putting this one. So be careful that never try to short circuit it. If you short circuit it, it's going to damage the power regulator. So if I do that, you will see it provides a good 12 volt. It hasn't touched properly yet. So you see currently it's 12.19 and it's a DC, so I put the switches to DC, which is here, voltage DC. So it provides a constant 12 volt. That really means it's good enough to switch on the system. So again, what you check here is that you need to ensure that the TX and RX is switched, and the Raspberry Pi power is switched on, and also the common ground is switched on. The rest of them, if you are not sure, just put into the 12 volts, because if you put 12 volts, the system wouldn't provide you 12 volt, which tend to damage the sensors. So now I'm going to switch on the system. So once you switch on, you just plug in. Remember that the positive is on the left hand side and the negative is on the right hand side, and you switch it on. And after this is being switched on, you will see that both the Raspberry Pi and Arduino has got the LD on. So that means the system is working. And once this is running, we could also do some quick tests as well. Let's say if you try to look at any pair of powers, so let's say power 36, it gives you almost like 0 volts there. So that's just a remnant power there. So that means the power is switched off. No power is supplied to there. And if you look at the reverse switches, because we don't give any commands, so that means the digital output is 0, you will see the 13 provides you a 5 volt constantly, because that's the reverse switch. So if it's off, that gives you power. If it's on, that doesn't give you power, right? And if you check the 3.3 volts, that is going to tell you a 3.2 something, so that means the system is good. 12 volt, right? So that's 12 volt and 5 volt. So that really means the system is working very well. And then we are going to try to connect to the system, right? Now, to be able to connect to the system, we discussed that there are several ways to be able to connect to it. The easiest way is use Bluetooth. So I've got a computer here, and it has a Bluetooth function. So I just right-hand click, add a Bluetooth device, and you will be able to find something. So this dot logger is called Pinjara 2. So I just pair with that by clicking this button, and then they start off the pairing process. And it might take a bit time, but as long as it's been paired, it becomes very easy to connect to it. So we could also prepare for a PuTTY. PuTTY is the system the system that you're going to communicate with the dot logger in general. So so this kind of connection will take some time, but we just need to wait here for a short while. So I can switch off PuTTY and wait until the connection is established. Amrit, have you got any questions?
Not so far.
Not so far? It looks good? Okay. So in general, if you want to use your hands to reboot Raspberry Pi Arduino, you can do it by clicking this button for sure. So you will see that the some other LEDs LED in the on condition. So that means it's properly booted. But I'll also show you how you can use command to reboot the system. And usually we can hook up to 60 or even 100 sensors, depending on the type of sensors, onto the dot logger, and we power separately. And separate power is really good, because if you power all the sensors at the same time, it just decreases the overall voltage of the system, and your measurement is not going to be accurate, particularly for the analog sensors. Also, we could try to start off doing some. Let me see whether the Bluetooth. Yeah, now it's connected, right? So the Pinjara 2 is now connected. The way how we need to connect to the system also requires us to join a personal area network. So if you click that button, then a window will pop out and you will be able to see a system called Pinjara 2. Even it looks like a speaker, but don't worry about it. So you just right click and then click connect using access point. You will see the connection successful. And once that is being completed, you could use PuTTY to connect to that. And there is a specific IP address 172.20.10 and 7. I think it should be 1 actually. I think it should be 1. Let's try and see which one is actually the right one. So if I connect to that, no, that's not really the one. Let's do that again. It should be here. Let's open it. No, so it should be 7. Let me try the number 7. It's a fixed IP address. No, not really. Let's have a look at the okay, so that's 172.20.1 and 1. Right, so let's try that. And if we're successful, we'll see a window like that. So you just click yes. And then you have your name and password. And you will be able to see a command prompt. That means your connection is successful, right? Now, this is the command prompt from the Raspberry Pi. So you are now connected to the Raspberry Pi. Well, probably now you think that, oh, I'm actually far away from the dot logger. I'm in the office and the dot logger is in the laboratory. So what are we gonna do? And actually, if you are working at the university, by default, we connect the dot logger into the edu ROM already. And this IP address is usually being sent to the ThinkSpot system. So ask your administrator to tell you what IP address is. So here we've got another IP address. So this IP address could be used on your PC. So you just need to go to your PuTTY, put into that password, and then you open it. You will see again this, and that gives you the same command prompt, right? But these two are different. So this is connected through Bluetooth. So you really need to next to the dot logger to be able to make the connection, which could be the configuration processes. Whereas this one requires a Wi-Fi to be able to connect to it. So you probably can use that when you are at office while the dot logger is in the laboratory. There is also a third option, which is that the dot logger is in the field. So in that case, we will have a dot logger connected to 3G, and then the dot logger will SSH into a server, and the server is permanently on. And at the same time, if you would like to access that dot logger, you need to first connect it to the permanently on server and then route it back into the dot logger. So this is what we call a reverse SSH tunneling, which we will discuss in another video. So nevertheless, we've now connected to the system. So congratulations. Now we can do some simple things here. So usually a few things we would like to do is to check around and see whether anything are expected. So because it's bash, then you can use general bash commands. So I'll show you a few bash commands here, which I normally do. So pwd is to tell you where your directories are. ls is to show you what is within the current directory. So currently we have these directories. right? Then normally we could use a command that is called that is inside the pyduino, which is the library, bash, right? And then if you use cd pyduino bash, you will see your working directory is moved from your home folder to another new directory, and you can use ls or even pwd to tell what is inside that folder. And now I would suggest you to go to Python, right? ls, and then you would have a utility, and you just use Python data logger v3 test. So if you run that command, you will be able to see a welcome interface, and that has got some basic commands for the data logger. So the first one is to check the handshake. So we are basically see whether the data logger is able to receive a handshake. So what does handshake means is that Arduino sends a command ABC. Sorry, Raspberry Pi sends a command ABC to Arduino, and Arduino will return an ABC. And if Raspberry Pi receives that ABC, that means the connection is perfect. So you see that the success handshake said receive ABC response from Arduino. So the connection between the two is great. So that's all good. So that's one of the checks that I normally do. The second thing, remember, we discussed before. Now, if you do a measurements, and the measurements are not successful, and that cause your Arduino frozen, and you need to reset your Arduino. So how can we do that? The way of doing it is to basically use the second command, which is called reset Arduino. So if I do that, you will see that the LED blinks. So that means the Arduino is rebooting. So I do that now. You will see currently the blink is on. That means the LED is blinking. So that means Arduino now is resetted. So sometimes this is useful. The number 3 is that I'm going to do a measurement from the onboard temperature and humidity sensor. So in that case, we will choose number 3. So if we do that, you will see that we've got the temperature on the room in the room is 24.9, whereas the humidity is 42%, and we can repeat that process, and you will see pretty much the similar condition. The also interesting part is that every time once we shoot a command from Arduino to Raspberry Pi, just leave there, that's okay. Just shoot a command from Raspberry Pi to Arduino, the LED tends to blink. So let's say I do a number 3 again, 3, 2, 1, go. You will see slightly blinking. So that means Arduino has received that message. So this is something that I would like to show. Also, we've got the Arduino sensors. So we could try to use Arduino switches. So let's say number 7, right? So duration of the switch stayed in seconds. Default is 5 seconds. Now let's try to change it into 10 so that we can test it. Amrit, I think you can just put these pins to any of the switches. Okay. So, okay, so now you connect that. So let's say 40. So you try to connect that to 40. Positive is on the upper side, and then negative is on the lower side. 40, 42, right? 42. It's a little bit inclined towards that direction. Yeah. So, but it has to be in a pair. Is that right? No, not that one. Not that one. Not that one. So let's say 1, 2, 3, 4. It is the same number. Let's say you put on the side. right? So that one, 49, and then this is 49. So currently the reading is a negative number, which doesn't really, it's a remnant of the power there. So I put 10 seconds, and then Arduino switches, then enter for, let's say, 49. And you'll be able to see that now 49 is high for 10 seconds. So currently it's still on, but later on it starts off dropping back. So because we run this command, it's running, it changes the switches from, it provides 5 volts to that pin for 10 seconds, right? Now we can do another one, let's say 22. We just need to move it, properly. So you just put in there. So now we didn't put the power on. That's why the voltage is just changing around some numbers. So we again do, let's say number 7, right? So we just say default for 5 seconds. And then let's say we're gonna power 22. If we do that, you will see that the power goes up to 1, 2, 3, 4, 5, right? So that's basically 5 seconds of 5 volt supply to switch 22, right? So that's a test. Now I'll show you how the reversed switch is working. So as we can see from the screen on the left hand side, here it's got 13, and the 13 has got the upper one and the lower one. Yeah, so just put in there. You will see now I didn't do anything, but the 5 volt is already there, right? If I do switch number 7, sorry, okay, so 7, and then I would like to switch off the switch 13 for 5 seconds. 3, 2, 1, go. Oh, sorry, this is actually the seconds, and then I can do the switch specific switches. So let's do 13, and then you will see that the switch 13, the voltage has already reduced to some random numbers here. So that means the switch is off at the moment. And also, because switch 13 is connected to the LED, you will see the LED is on. So that's basically how the switch works here, right? Okay, so that's basically a very quick way to test the system using a quick interface. And if you would like to exit, you could go X and X, so you left from there. Now we're going to go a bit tech. We're gonna work with script instead. So if we're gonna use script, I would recommend you to go to pyduino hydrogeologger, and you will be able to find out our library. I would like you to go to wiki, and you go to the setup tutorials, and in here you've got quite a few commands here. So you could run this one, right? So you just run this command here by right click on your command prompt. Then you will be able to, no, this is bash session, Pyduino, bash, serial session. Now you've got this. Now they got some kind of quick tutorial. So now I'm sending a ABC. You will see it returns a ABC, right? Because I'm talking to Arduino, and then Arduino returns a ABC. That means the handshake is correct. Now, if you would like to say measure analog pins, right? So one of the analog, as we discussed, is to measure the voltage from a channel. So what we could do is this command, you shoot it in. So what does this command here mean is that you are measuring the first analog channel using power port 22 to supply power and measure 5 times. And before measuring the 5 times, you do 3 measurements, but you throw it away. The reason is that usually the first few measurements might not be consistent, but after that it becomes stable. And the interval millimeters means that what is the time interval between the neighboring measurements. So this one by default would be 10 milliseconds. And the debug one is to provide some outputs similar to the ones that you inputted. So currently you see that the debug is actually, the result is 694. So if I run that again, I guess that is still a similar number. So this one is moving around. The reason this one is moving around is because it basically measures the error about analog. So it doesn't give you a specific good consistent reading. But I can make a very quick example. So let's say we've got a tiny little cable, and I can connect the number 1. I can connect the number 1 to, let's see where it is here. Okay, so I could provide a, I could provide a, let's say voltage. So this is channel 4. If I provide a channel 4 to a, let's say 3.3 volts to ground, let's say to ground. So we basically connect the channel 4 permanently to the ground. And then what you can see is, so we use a separate text editor, Notepad++. We just got so many other things here. So we basically measure analog 4, right? And what you will see is that it constantly provides a 0 reading, right? 0. Why? Because it's connected to the ground, right? Instead, if I connect this one to 5 volts, for example, where can I get a 5 volt? So here is a very important thing. You see that the 12 volt are very close to 5 volt. If now you connect the 12 volt to the analog channel, this system just damaged straight away. So be very, very careful. Try not to connect your analog into a 5 volt. So in that case, I probably will we need to be very careful. So in general, what we would like to do is to cover the 12 volt so that you never be able to connect that channel to 12 volts. So now I'm kind of very safe. So I can connect that to the 5 volts. Right, okay, so now if I run the same command, you will see that gives you 1024, right? 1023. So what does this mean? Well, it's very straightforward. So if it gives you 1023, that means it's 5 volt. If that gives you a 0, that means it's ground. And that spans from 0 to 5 volt, so it's a linear correlation. So you can work out if it's 512, that means it's 2.5 volts. So that's the linear correlation. So that's basically the analog channels. What does the analog channels do? I think right now it's a good time for us to be able to connect some of the sensors. So let's switch this off for now. So be extremely careful that don't connect the any of the pins to 12 volts, because if you do that, the system is going to be damaged. The second thing I would like to do, I would like to show you is that before you start off connecting any of the ports, you need to ensure that you are inserting to the upper part of it rather than the lower part. And let's say take this one as example. Can we see that? Okay, so you need to basically scroll it anti-clockwise to allow the whole, the entire hole is able to, is visible. And then you start off scroll clockwise to be able to clamp your cables in, because sometimes you are clamping not within the square box and the measurement is fake, and you're looking around and see whether the connection is smooth or not, and turns out it's just a fake connection there. So always ensure that before any connection you have a holes there readily to insert your cables in, right? So that's very, very important. And now I'm going to introduce some of the sensors that we normally use. So the first sensor I would like to introduce is a soil moisture sensor. So this sensor are also developed by us, and that measures the box soil moisture content, and through a method of dielectrical permittivity. So what is dielectrical permittivity? It is the same as how your screen is able to identify your fingers. The general way, the way it works is that the dielectrical permittivity of water is 80, and the dielectrical permittivity of soil is 15, whereas the dielectrical permittivity of air is 1. So, so that you have 0 to 80 to be able to tell what is your moisture content. But also bear in mind that the soil has got a permittivity of 15. So different types of soil will give you different types of background measurements. And that background measurement is depending on the mineralogy. It could be depending on EC. It could also be dependent on the temperature. So in general, the soil moisture sensor does not have a one-to-one moisture adjustment. Instead, it gives you a full range, and it's the user to be able to tell what is the current moisture content based on the reading there, because that value is subjected to change. So this sensor is using analogs. So in the analogs, we usually have 3 types of cables, right? So 3 cables. So the cables got positive and negative and data. So usually we wire the system in a color code. Red is always positive, and black is somehow related to negative or ground, and the data is black. So you're just assuming this is always the case.
White.
Yeah.
Data is white.
Sorry?
Data is white.
Yeah, data is white. Yeah, data is white. Yeah. And sometimes some of the sensors is cabled in the wrong way, so you need to be very careful when you start wiring. But in general, you could assuming positive is red, black is ground, and data is white, right? So I'm going to allow you to hook up on. So we probably hooked up to switch 22, and then say analog 2, right? Okay, can you do that? Yeah.
Analog which one, sorry?
2, let's say 2. Okay. Right. Yeah. So before you put it in, you need to ensure that you do it anti-clockwise to open up the hole and insert that sensor. Right. Yeah. That's good. Yeah. Okay. Analog. Now, the second is 22. So again, anti-clockwise. So that's the positive pin. And put it in. Yeah. and the negatives. So usually you try to pull out and see whether that's stable. It seems to be quite stable, so that means it's a good start. We put the sensor on the screen as well to give a reference right now. Okay, so remember that we put the analog, so we have a text to play with. So the analog is going to be 2, and the power is going to be 22. And we're going to do 5 measurements, and we just need to do 1 dummy really. And then let's put the interval as 100, right? And we can say debug is 1. So that will return whatever we put it in. So we copy the whole thing, minimize it, and then right clicking here, you will be able to see that later on you get a result. That's 800. 800. Is that 2? Yeah, it is 2. It's 400. That seems to be quite high. Nevertheless, the values seems to be quite consistent. Can we just put it in here and see? Right, so that's 400. How about if I put my hands on? So it seems not quite working here. So probably we had exactly the same issues as we did before. Are we using... So we just changed the... So we first opened it up completely and then put it in. So I now change the analog from 2 to 4 and try to do that again. I'm not sure whether that's the connection here or some other reasons. So now we've got a 100, right? 105, right? So 105, very consistent. But if I put my hands on and I do that again, you will see the number increased to 300. So this is an indication that the sensor is able to tell the impact of the hands on the dielectrical permittivity, right? So if I again release my hand, you will see the number goes back to 100 something. So we basically have got 200 point to be able to tell from a completely dry condition to a wet condition. So that's how the sensor works here. So that's the number 1 sensor. So you could do that in a sequential, many sensors. All the switches are here and you have your analog there. So you can put up to 16 moisture sensors there and you can do that sequentially. So that's the first sensor I would like to introduce. Now let's move to a second sensor, which is what we call a suction sensor. Right, can we take this out? Probably we have another suction sensor here. Okay, so we can use this one. Now, this is also a very commonly used sensor, suction sensor. So what is suction? So suction is to give a soil suction a quick, kind of intuitive features. We would say that if you put a dry towel into water, and what you will see is that the water starts sucking up and make the towel wet. So that's literally the suction. Soil has got the suction when it is partially saturated, and this can be measured. So this sensor measures the suction. How does it measure is that it produces the heat, and this heat will obviously heating up the ambient environment. But the heating up is not going to go crazy, let's say heating up to 100 degrees Celsius around it. No, it wouldn't. Because at some stage, the amount of heat produced is the same as the amount of heat dissipated to the ambient environment. And that delta T is important because imagine if your soil is very dry, like a ceramic, the heat does not dissipate, so your delta T is significant. Whereas if your soil is very wet, water is very conductive in heat, so that the amount of heat accumulated just dissipated very quickly. So the delta T is very, very small. So we basically use the delta T as the static condition to be able to tell what is the moisture, what is the suction condition there. So because heat and suction has a direct correlations, and we need to fit against it. To use this sensor, it's important that you need to water saturate the ceramic in the first place. If you don't do that, the air gets entrapped inside, and it constantly measures a dry condition. And usually the wetting, you either put it into a suction chamber, or you soak it in water for roughly 7 days, and you will see the delta T is being changed over time. So please do not directly use this sensor at a dry condition when you want to do a measurements. Really need to ensure it's reaching an equilibrium to the ambient environments. Now let's looking at the cables. So the cable, instead of having 3 cables, now we've got 4 cables. Why do we have 4 cables? I'll explain. So first of all, you've got positive and negative. So this positive and a negative is for the temperature measurements, right? You basically warm up the sensor. You basically provide power for the temperature elements, right? The number 3 is the white one. So the white one is the one that measures the temperature. So once you got these 3 well connected, you are able to measure temperature from the sensor. But now there is an extra function, which is to heat up the sensor, and that heating up is done by this green pin here. So the way how we're going to connect that sensor is to hook up. Where you do that? Yeah. Is to hook up. We can hook up these ones first. So yeah, positive and negative. And you also need to put this one in, the tiny needle, along with the positive. Yeah, do that please. Yeah, in anyone, let's say 23. If you want me to hold it. Yeah. So again, first, anti-clockwise to give the hole available for the pins to get in. We could just lift it, so it's easier to put the sensors in. So you insert it. Just try to push it in. Yeah, push it in. Usually you can't really see the metal things if it's inserted properly. Yeah, just try to push it in. You can first push in the red thing, and then yeah, okay, and then try to sneak in the black one. Yeah, okay, now it's the time to put it in. Yeah, okay. Then the negative, yeah. So actually it's a good habit to do it the bottom one first, because that gives a little bit more space. Yeah. So you can insert that. We don't really have much space.
Yeah, I should have inserted the bottom one first.
It's also a good idea to insert the bottom one in the first place. Right, okay, now it's the digital pins. So the digital pin needs to go along with these. So you can put it into, let's say, sensor 50. Sensor 50 is here. So you unscrew it first. Yeah, I'll put this one in first, and then we probably need to go Okay, so now it's sliding in, and okay, this side sliding as well. Okay, so now screw it in, right? And so that is giving a proper temperature measurements. Now the very final one is the heating function. So the heating function could go next to it, which could be the number 24. So you unscrew it first. Okay, and then screw it in. Yeah, okay. Now it's well connected. One thing I have to mention is that we actually have got the extra cable between the two, between the power and the measurement for the temperature. And this is because that sometimes if the cable is too long, the signal to receive temperature measurement becomes weak. So you just connect that pin to the power to boost the signal from the digital measurements, right? This resistor value is subjected to change depending on how many sensors you connected to the specific digital pin. So this digital pin can connect many temperature sensors at one time. So the more you connect to it, the lower the resistor is going to be, right? So now we're gonna try to do the measurements. So the way how we do the measurement, according to the guide, is going to be used the Fred sensor. So we find out the Fred, F-R-E-D, right? Let's just try to get Fred, right? So before we do everything, we need to find out an address for that sensor. So we need to find out the sensor address, right? We copied here. Now remember that we put the digital pins. We put the digital pins at pin 50. So that's pin 50, right? That's pin 50. So that means we're gonna search all the sensors at channel 50. And the power for the temperature sensor is 23, not 24, not the one in blue, because the blue one is for heating up the sensor. So we're not heating up. We're basically connected to 24. So the power is going to be 24. So what does this guy do is that they try to find out all the sensors that is connected to pin 50. So let's do that. If I click that, you will see it ends up with, oh, it hasn't come up with anything. So that means, no, that's wrong, because I'm shooting up power to 24, which is for heating up, and that's not heating up. So we need to change that to 23 instead, right? And then let's do that command again. You will see some of the interesting reading. And what does this reading mean is that you first find out a string here. So the string here is the IP address of that sensor. And you also got the temperature is 23.62. 23.62, so that's pretty consistent, and they all coming from that temperature sensor. And we basically use this command to be able to identify the IP address for that specific sensor. And remember, this digital channel is able to link up to multiple temperature sensors at the same time if they are all powered up at the same time, right? So it's important. So if you put two sensors and only power one, sorry, you might not be able to find out the one that is not powered, but you are able to find out the one that is being powered. So you can have multiple temperature sensors located in there. So currently we've got that IP address, so I'll paste it in here. And now I need to slightly revise the Fred sensor. So the Fred length sensor, which is in this slide, and we've got Fred, right? So that's basically the command. So Fred, then the IP address. So we need to first pad all the channel or the digital IP address with 0. So usually comes with pairs, and if it comes only one single one, that means you need to put a 0, right? So if it's A, then it's 0A, it's not A0, right? And then you delete all the spaces in between, right? And put it in here, copy, paste, right? What is the digital in? And from here, that's 50, right? That's 50, so 50. Okay, sensor power, that's the pin that powers the temperature sensor, which according to here is 23, right? What is the heating power? That provides the heat. That is going to be 24. Now, ITV is interval. And what does interval here mean is that they would first do 5 measurements, and in between the 5 measurements, you allow it to hit for, the measurement in between the two is going to be 1 second, and there's no debug. So that's what the sensor does. One thing I have to say is that if you write here as 5, you will see that you will get 10 data, because the first 5, the sensor will be powered only for 5 seconds, because that's 1 times 5. And from 6 to 10 seconds, the heating element is going to be switched off, and you can see how the temperature gets dissipated over time, right? So you will, so again, if you put 1005 here, that means overall you will heat up the sensor for 5 seconds, and during the heating time you will have 5 measurements, but the outcome will get 10 measurement. The last 5 measurement is to see how the heat gets dissipated. So that's what this command does. We shoot that command in, and you'll be able to see the temperature. This is a constant temperature still. It started rising, see? It's 24 now. It's 24.737, 75, and 25, 112, 31, 37, and 25. Now it's reducing. So it started reducing, but it happens a bit later than the moment when we switch off the heatings, right? So now this command is only for us to do a test. And if you want to do a measurements, if you want to measure suction, how long do you need to do, what type of parameter you need to do? You need to convert this into 6 seconds at least. So what does this what does this mean is that 6 seconds times 5 is 30 seconds. So that means within the first 30 seconds, the sensor will keep on heating. And you measure the temperature every 5 seconds, every 6 seconds during the heating. And after the heating is completed, the heating function will be switched off, but the measurement will keep going, and you will be able to get another 5 measurements, which is to see how the sensor temperature gets cooled down, right? So this is what we're gonna see. So again, you will see a temperature that is a background temperature. And then later on, you will see another one which has a significant heating up. And then you will see again a bit more heating up. So now it's already nearly 2 degrees Celsius, the difference. And you actually are expecting more. So this is 26. So this is 1, 2, 3, 4, 5, 27. So that's already 4 degrees Celsius, the difference. And 28. So that's 5 degrees Celsius. And sometimes if you touch the sensor, oh, now I can't really feel the differences at all because it's inside. Yeah, so if I can't really feel the heating element because it's inside the ceramic. But now you see the temperature started falling down, right? So in general, if you look at this one, you plot it, you will see the temperature goes like this and then going down. Are we reached a steady state condition? Not yet, not yet. Because if we reach a steady state condition, we probably will see that the temperature reach a plateau, but we haven't seen this. So roughly 28 is the highest temperature. So how should we do that? In general, it will take very, very long time to be able to reach a steady state condition. And that will require a lot of power because you are literally heating up the sensor. So there is a consensus that we try to heat up the sensor for 30 seconds and try to measure the temperature after 30 seconds of heating. So that's going to be the 6th. So this is the initially, 2nd, 3rd, 4th, 5, and 6. So 6 is pretty much like a plateau, as you can see, right? So you use this one, subtract by that, this is where the delta T is being used. And you use that delta T to tell what is the suction here. And here I can say, because it's 5 degrees Celsius difference, that means the suction is very high. Whereas if we put this sensor into water, then the temperature rise would be only 1 degree Celsius or even less, right? So that's what the suction sensor works. And you can do that in parallel. So if I would like to do this, then I could have, I first of all could connect, if I would like to have 2 sensors, then what I'll do is that I will connect their sensor power, the sensor power to 1 switches. So this 1 switch provide powers for 2 temperature sensors, and also their digital pin goes to the same channel, so 2 pins together, but their heating element will be at separate location. So that means, so if that's the case, if there is a second sensor, I would like to make it in this way. So unfortunately, the IP address is going to be different from the first one. The digital in is still 50. The sensor power is still 23, but the heating power is going to be 25. So by doing that, you could have a second sensor, the second sensor, do another temperature measurements. And that saves an extra channel for you to switch on temperatures. You could have a separate temperature in a separate channel, but that occupy extra power ports. So you can save some power ports for some other uses, right? So you have a question here? Or?
Yeah, like previously we used analog for moisture sensor.
Yeah, yeah.
And now we switched to digital.
Digital, yeah.
And
what's the difference between the two, right? Okay. Analog means that you basically measure the voltage difference. So it's something other things could measure. Digital actually transmit the data through a string. So the sensor itself has already got a chip. They measure the analog. They have already measured the temperature through an analog, probably analog way, and convert that analog to a digital string and send the string to the downloader, right? So you basically receive 0 and 1. So that's the digital. So the difference between the two, actually, there's another layer of differences. So usually for the digital sensors, the measurement becomes somehow independent from dot logger. The dot logger is basically record 0 and 1, that's it. But for the analog sensors, the dot logger needs to ensure that their power is somehow being regulated so that the reference is always the same. So the digital ones, they probably has embedded some kind of voltage regulator to ensure the voltage, the reference are always the same, right? Whereas the analog ones, the dot lower really needs to give a consistent, the consistent power to ensure the measurement is in the same level, right?
And is this the only board that supports digital data?
There are quite a few. So all the analog ones can be used as digital as well. The 50, 52, 453, and 51, 53, those ones can be used for that. But I would like to say that the 50, 52, 51, and 53, this 4-channel has a special function which we write it here as SDI12. SDI12 is one of the most popular protocol used for environmental sensors. Yeah, so we will now introduce a SDI12 sensor. Right, so this is a commercial sensor. I think some people will know what that sensor is. So we've got the pins here, yeah. So this is the MITRE 3 moisture sensor. It's relatively bulky, but it's a legacy sensor. It's been in the market for a long time. So I don't need to open it, but you can see they've got 3 pins already here. And what does this sensor measure? 3 things. Dielectrical permittivity of the soil, which can be converted to moisture content, temperature of the box soil, and also EC of the box soil. The EC is related to the salinity of the box soil. So you are able to measure 3 things. This sensor is pretty good because it's very stable. It could be in the soil for a long time, be able to measure the results, quite reliable. It's a little bit too bulky, particularly if you want to deploy the sensor near the surface to measure the actual evaporation. So actual evaporation will require a moisture content near the surface, and if this sensor is too bulky, you just measure it at too deep, so it's not representative to the surface condition. The other thing to be careful when using this sensor is that although the pin appears to be where the measurement is taking place, in fact, the whole body is also part of the dielectrical permittivity medium. So you need to put the whole sensor into the soil to be able to get a representative value, rather than just expose the handles outside of the soil. This also applies to our moisture sensor. So I would suggest you to put the handles inside the soils as well, because this is also part of measurement medium as well. If you really want to use the handle, you need to do a proper calibration, same to this. And this sensor,
One more thing I'd like
yeah,
to add.
yeah.
This one has a very pointy and sharp tip. So
Yeah, be careful, be careful. Yeah, be careful. This looks like a needle, really. Now, if you look at the input, you've got, I think that should be that one. Yeah, you've got three. Yeah, 3 cables. So again, if you look at this, you pretty much know this could be positive, this could be negative, and this could be data, right? And the connection is relatively straightforward. So we put these 2 to the switches and the 1 to the digital. So we can try that. Yeah, so let's do that. Again, you unscrew it a little. You unscrew it. Do that one. Yeah. So for SDI12, yeah, now you're screwing. Let me just, yeah, okay, go. For SDI12, you could put it into channel 50, 52, 51, 53, and analog 8 to 16. So all these ones are able to use to hook up SDI12 sensors. And the other important thing I have to say is that you again can put multiple sensors into one digital pin, and they are able to differentiate each other because every sensor has their own IP and they only send 0 and 1, the digital input to. So you are able to, the dot logger is able to differentiate them. Now you can put the channel, let's put it into the other one. So can you unscrew it first? Let's do the bottom first. Yeah, okay. Okay, go. Now it's good to go. Okay, now you've got another one. So you see there is a line. The line gives you an indication that they are in pairs. Okay, now you put it back in. Yeah, it's that looks good. Yeah, right. And I just put this one slightly aside. Again, gives us a update. So in here, we have the sensor connected to digital pin 52. And the power control is done by switch 26. Yeah, 26. So we could first get that command, which is here. Right, and then we prepared it here. And then what we've got is what the 52, right? The power is going to be 26. And we would like to power off the channel after the measurement is completed. And the default command is to read the results. And we want to give some extra things, so we just put the debug one. So that's the command. And we copy it and right click on the command input. You will see later on some results coming back, hopefully. If not, then we need to find out whether the cable connection is stable or not. So we haven't seen anything. Oh, right, so you see you've got a sensor. So number of sensors, this is not no sensors, the number of sensors, 1. The address is C, and MET means the type of sensor. So this sensor gave its name as meter 3, perhaps that's called MET. And they provide 3 measurements, 3 types of measurement. One, this 1800 something, this is the dielectrical permittivity. So usually if it's dry, it's 1500. If it's wet, it's 3000. So currently, given that the sensor is in a plastic, so it gives some background dielectrical permittivity. That's why the value is 1800 something. The temperature is 24°.1. And the EC, electrical conductivity, is literally 0, right? So we can shoot exactly the same command and they should give us the same thing. Also, I would like to give one extra note is that sometimes if we Control C left from this and then go into the serial session, I would like to just do some ABC first. You see, currently we lost A, but we get BC. So I would like to basically try a few times to ensure that the connection between the two does not any missing point, right? So then we can prepare all the commands and then basically shoot all the commands. So now we have the moisture sensor that works, which is pretty good. Now, what other sensors we have? So we have this sensor, and do we have any other sensors? This one is completed. I guess that this sensor is completed. Okay, so we are almost finished. Before we finish, we check out. So I would like to show the very last sensor, which is a temperature humidity sensor, right? So this sensor has got a chip called SHT71. And this sensor measure temperature and humidity in the air around us. So it's relatively similar to that sensor, but this sensor, as we said, is designed to measure the temperature and humidity inside the enclosure, and this one could go outside to the ambient environment. So this sensor has got, interestingly, has got what? 4 pins. That's a bit strange. You know, usually we got 3, now we got 4. Well, the suction sensor has a clear reason of having 4 because you need to have a separate power to it. But why this guy has got 2? So, well, again, let's differentiate these two. So these two obviously are power and ground. And these two are basically 2 digital pins that are able to get the data out. So they are using I2C protocol, which will be used in this section. So we use the analog, we use the digital, and different protocols. So this guy speaks analog, this guy speaks SDI12, this guy speaks one wire, so that's a separate language, and this guy speaks I2C, right? So you see so many different sensors, they all speak different languages, but I don't care. I just need to find out the right manuals and see what type of language they speak. We just say this communication, we use this language, and the data logger is able to tell, right? So now let's hook up the sensor. So we first go the ground could go 30. So again, unscrew 30. Yeah, so that's 30. Yeah, and then put it in. Yeah, that looks good. Then we do another one. Not that one, not that one. I think it's good to go. Yeah. Now, it's important to let out everybody see, to be aware that you are able to tell the alignment by looking at the line in between. So they are always in a pair, right? So if you look at 30, you really need to ensure that the negative goes to 30 as well. If you put the positive to 30 and negative to 31, it's not going to work, because the ground, this is not ground. The lower switches are not ground. So they are always segregated to the environment, to the ground, if they are not connected. So be very careful on that. So usually SDA is green. So we put a SDA on. Yeah, now put it back on. I2C. Okay, now we got a 0 here. So hopefully this one is good enough to, yeah. I think you just directly go to hook it up, yeah. No, it doesn't work. So you unscrew it first. Right, so we screw it in, we put it in. Okay, now screw it on. Okay, good. Okay, so that connection looks quite stable. So as a summary, the I2C, the digital pin is connected to 0. And the switches are in 30, right? And similarly, we have a search function designed for the I2C pins. So I2C. So we just need to shoot a command. Search. I hope that well, this search might not work if we didn't power a specific channel. So if we're gonna do search, the first thing we need to do is to we probably doesn't need to do a search. Let's directly go for the I2C. So we need to, because this is the SHT sensor. So this is the command we would like to go. So that's the command, right? So what we have here is the 9548 is the multiplexer for the I2C, and the specific channel we put it on the sensor, as we know, is channel 0, right, which is here. And the type of sensor is SHT, so we basically use SHT. This is 31, but 75 sensor also works for that sensor. We want to do 5 measurements, probably do 1 dummy. The interval between the two, I would say 100, right? Does it say the power? It doesn't really say the power. Okay, so we need to give a power on for that sensor. So it's a little bit tricky here. The I2C pins, even you got 7 channels, all the sensor needs to be switched on at the same time to be able to measure from one sensor. So this is a specific requirement for the multiplexer. So the multiplex. So basically, Arduino only provides one I2C channel, but we sometimes feel it's not enough. So we add a multiplexer, so that we will have 8 I2C sensor to be able to install. But there is a condition, which is that if you have 4 sensors connected to the multiplexer, they need to be powered on at the same time. So you can't just power one I2C sensor and having 8 sensors input in there. So if you have 8 sensors put in here, the 8 switches need to be on at the same time. So the whole I2C is ready for you to do the measurement. But there is one thing I have to say. I2C is sometimes not stable. Let's say within the 8 sensors, if you have one sensor that short-circuited, that means the rest of the sensor is not going to work. So be very careful when you decided to use I2C sensors. And also be careful when you use any types of digital sensors, because if you put multiple digital sensors into one measurement pin and one of the sensor gets short-circuited, you probably doesn't need to have to get the result from that groups. You have to rely on the rest of them unless you are able to identify. There's also one important thing. You probably have a question. How can I connect the 8 sensors or 10 sensors into tiny little small hole here? It's a good question, actually. Usually once this dot logger is into a enclosure, the enclosure will have one thing called DIN rail. So we can search the DIN rail to give you a show. So the DIN rail looks like, this is not really the normal DIN rail that we normally use. So this looks like a DIN rail. So what this guy do is that these all tracks are all interconnected with each other. So you can put that particular pin to this side and then rest of them connected to it. So this is also a DIN rail, and that's the DIN rail. So usually if that looks like that, I will assuming all the blues are all interconnected, all the reds are interconnected. So you connect that specific pin to there, and then you have multiple tracks to be able to connect to that. So this is what the DIN rail does, right? Now, so that if we want to measure that specific channel, what we're going to do? We need to power the port 30, right? So again, let's do a measurement. It's a good time for us to do a measurement. So you can put your pins on 30. So you put on the head, right? I also can show that number there. So have you got enough space to be able to do that? Yeah, do it very carefully. Now you see that the 30 does not have anything. So if you would like to look at the power function, So we've got power switch, power switch, yep. So this is the power switch command. So what is the channel number? 30, right? Yeah. So if I shoot this command, you will see that it just simply power on the channel 30. That's it. So I power that. You will see, no, it doesn't come up. Oh, right, okay. So this says that the status is 0. So I need to give the status as well, sorry. Go back to this, and then power switch status is 1. So I need to put this section here and put 1 single comma. Okay, so that will switch on the power. So we go here, here, here. You will see you get a 5 volts as indicated by the voltmeter. So if you have multiple I2C sensors, you need to power them on in the same manner. So you can leave it there, and then you can use the command 9548 search to be able to find out all the channels that are connected with sensors. You see TCA port 0 that has found 1 sensor. 1, 2, 3, 4, 5, 6, 7. No sensors at all. So you know that sensor is connected.
How to power all the
sensors? So that sensor. So if you have multiple sensors, they go to separate digital pins, digital switches. You just run this particular command multiple times. Yeah. Well, if now you are basically debugging it, you need to do that one by one. But once you're using Python, you can basically just do that in a sequence. And that's pretty easy, yeah. So, and the way how we hook up the sensor is that you will see eventually this list shows all the commands that measures all the sensors hooked up, and later on, once that's summarized, you put everything into a Python code and repeat that all the time, so you can do the regular measurements. Yeah. So this is also good for us to know what type of the measurement we need to do. The 9548 search, that is not important for you to do the regular measurement, but it's good for you to find out all the sensors, right? So once we find all the sensors, then we can tell them, you see that this particular command, they say that read from channel 0, it's a SHT sensor, measure 5 times, 1 dummy, get rid of the first result. And in between all the measurement, the time interval is 100 milliseconds, and show all the results, all the input as well. So we shoot that command into the system, and you'll be able to see some of the interesting results. So 24 degree, that's the temperature, 49 is humidity, temperature, humidity, temperature, humidity for 5 times, right? So now you see, we've already did a sketch, so many things here. Okay, before we wrap up today, one of the important thing here is you need to switch off the channel for the I2C. So you can repeat that and then put the status to 0, right? That's a very important thing that you need to do after the loop, particularly for the I2C, so that we check it out. So now if we look at the processes, we got quite a few sensors connected. We got the individual commands that are able to do the individual sensors as well. And we can shoot up any sensors. Let's say now I decided to measure a temperature and a humidity sensor. We just go there and then shoot that particular command in there. Then you are able to measure the temperature and everything. And you basically try to put all the sensors one by one, test one by one, and then end up with your system. And then you write the script to repeat this type of measurements, and you close off. I wouldn't recommend you to try to hook up all the sensors at one time and then try to individually debugging it. That becomes very complicated, because if you do that, you know some sensors work, some sensors doesn't, right? So always do that progressively. I do have another script that will tell you how you can put all those commands into one Python code so that they can cycle and send it online. So I'm not going to introduce this for this video. Amrit, have you got any other questions?
Should be all good.
Should be all good? Okay, I think it's a matter of practice. And we are now trying to further reduce the size of the dart logger by almost surface mount everything by machines. So producing a dart logger is pretty much like a printout A4 paper, so that we can somehow further reduce the cost of this dart logger and make it easy to use. So that's pretty much a video today. Thank you very much.